Hi, my name is Shay, a PhD candidate at Tel Aviv University, and I'll present our work on motion deblurring using spatiotemporal phase aperture coding. Motion blur limits the exposure time while capturing moving objects. It is vastly researched both in conventional image processing and computational imaging. In this work, we propose a motion deblurring method based on spatiotemporal motion coding. We capture a scene containing moving objects using a spatiotemporally coded camera that embeds color motion cues in the intermediate image. This image is then processed using a CNN trained to utilize the embedded color motion cues to deblur the image. The coding is based on a phase mask incorporated in the lens aperture. In previous work in our group, a phase mask is designed to generate focus-dependent color cues in the captured image, enabling both extended depth of field and depth estimation from a single image. The phase mask is composed of several rings, and it is designed to generate a color-dependent PSF for each defocus condition. These color cues enable defocus estimation, which is directly related to depth, and also help restoring the blurred image. In this work, we use a similar phase mask to encode motion cues and enable blind motion deblurring, but with a significant difference. Focus variations are introduced during exposure, what leads to motion encoding. In our system, we assume an infinite conjugate imaging setting. If a point source is moving during exposure, it generates a trace in the acquired image. If we add a focus variation during exposure, a spatial blur will be added to the trace. However, if we incorporated the color-defocus phase mask in the lens and perform a similar focus variation, the resulting motion trace is colored, thus containing cues to both motion direction and extent. To train the motion deblurring CNN, we generated a dataset based on the GoPro dataset released by Na et al. Each image in the sequence is convolved with the instantaneous colored PSF, and then the images are summed up to generate the motion-colored image. After training led to encouraging simulation results, we turned to build the setup of our coded camera. We used an imaging lens equipped with a liquid focusing lens and incorporated our phase mask in its aperture. The liquid lens is synchronized to perform the designed focus variation during exposure. As a first test, we validated the PSF encoding. An image of two rotating white LEDs was captured, and the color-coded PSF pattern can be clearly seen. The blue-green-red transition indicates both motion direction and extent, thus allowing blind shift-dependent motion deblurring. To check our deblurring performance, we performed experiments with a moving object. Our results are compared to an image acquired using a conventional camera in the same setting and deblurred using the CNN of Na et al. In an additional test, a rotating photo is captured, demonstrating the deblurring performance of motion in all directions and various velocities simultaneously. In the following zoom-ins, you can see different areas in the image which correspond to different motion direction and extent, and the significant difference in the deblurring performance compared to the reference method that doesn't use any coding. To conclude, our joint optical digital processing scheme is based on color motion cues embedded in the optical image, which enables shift-dependent motion deblurring without a limitation on the motion direction. For further details, you are invited to read our paper. Thanks for watching and have a nice day.